Well, as I promised to you that I will come with another video on the combination and sequential circuit. So I'm in front of you. Before starting this video, let me introduce. I am Combinational, as you know very well. So we already had one video on basics of digital electronics, and you can go in the playlist and can check out. I already shared one video on the multiplexer. How can we make multiplexer on Tinkercad? Today we are going to talk about combination sequential circuits. So many of you might having a doubt in mind that what are these combination sequential circuits. So if I don't go in so much deep knowledge of this and just give an overview, you have to understand one thing, that combination sequential circuits differ in the case of memory. Okay, so when we are having a memory, we talk about sequential circuits, but if we say that we don't have a memory, we talk about combinational circuits. Nowadays we are living in a digital world. If you talk about the biggest invention of 2021 or 2020, 2019, 20, 21, 22, the QR code. Nowadays, one of my student come to me and say, sir, we designed an app, and the QR code is there, everything is the QR code, just scan it and you can use it. We are dealing with disruptive technologies, we are dealing with AR, VR, but what is the basic, what is the background of those? The background is nothing but your digital electronics. The background is nothing but your 0 1. What we talk about binary, what we talk about, that if you talk about language of the computer, is nothing but hexadecimal. But we have to understand that combination sequential circuits are the backbone of any digital circuit. Okay, whether the positive logic or a negative logic. I already discussed in my previous video about positive and negative logic. You can go over there and you can check out. And still, see, I want to say something, that if you have any doubt in understanding the topics, understanding the concept, you can write in a comment. I would be more than happy to answer your queries, right? So without wasting more time, that I'm coming to combination sequential circuits, I already discussed with you all what is combination circuit, what is sequential circuit. If I talk in a brief, the combinational circuit are those circuits which are without a memory, and sequential circuits are those which are with memory. So you can say that sequential circuits is nothing but a combination of combinational and memory. So in front of you, you can see there are n number of inputs and we are having a m number of outputs. So we can see that in a combinational circuit, we go with a universal gate. I already discussed in my previous video that what is universal gate, what are basic gates, and how these different types of gates are segregated on different types of inputs and output, right? So we can say that in the combinational circuit, any output of the combinational circuit at any instant depend upon the present input value. I'm again repeating, the present input value. Now, if I talk about present input value, you have to understand two things, students. When we talk about digital and discrete, there is a very thin line difference between both of them, digital and discrete. Discrete is the original form of signal and digital is for our convenience. I already discussed in my previous videos when I talking about multiplexer and the basic concept. The analog is more stable as compared to digital, but digital as per for our convenience. I hope I make it clear. So the combination circuit is basically where the different gates are combined together to give a certain desired output, but the output depends upon the present input value. So it doesn't require any kind of memory. That's why we're talking about present. Otherwise, if you're talking about past input level, we have to go in a case of sequential circuits. Okay, these circuits can have multiple number of inputs, multiple number of outputs. We will see in a later video. Sorry. So if I talk about sequential circuits, we know, as you can see in a figure, the sequential circuit consists of combinational plus memory element. As you can see over here, we are showing a memory element and in a feedback form. But when we talk about memory, we're talking about clock. As you can see in your house, when you're using a clock, okay, it's a synchronized way. We will talk about in a detailed way in a video. But yes, when we're talking about memory element, we're talking about clock. right? So yes, it has a memory. The output can vary from various inputs as well. It consists of memory element, it consists of output, whereas sequential circuits require input clock. We will talk about flip-flop and latch also in the video. Many of you might have a doubt in this, and many students ask me whenever I talk about digital electronics or different type of circuits. See, flip-flop is a clogged circuit, where the latch is not. In simple way, in a layman language, we can say the latch is uncontrolled kind of circuit, but the flip-flop can be controlled. You can see the very different examples we have in a sequential circuits. They can be synchronized, they can be asynchronized, or synchronous sequential circuits or synchronous sequential circuits. We will talk about in this video about flip-flop, about latch, about resistors and counter type of sequential circuits. In the combinational circuits, you can go to my video. I already designed about the multiplexer using Tinkercad. Similarly, we can design a demultiplexer, decoder, encoder, half adder, half full adder, half subtractor, full subtractor. If any of you feeling uncomfort in making any kind of this circuit on Tinkercad, please write in a comment so that I can post another video for your convenience, right? But yes, multiplexer, the many students put in query for the multiplexer, so I put in video for the multiplexer. Now, combination logic circuit, as you know very well that we are having a arithmetic and logical function. We are dealing with data transmission and we are dealing with code converters. See, when I'm talking about arithmetic and logical functions, I'm talking about ALE, which can be your array, which can be your comparators, which can be your subtractors, which can be your adders. Similarly, for data transmissions, we talk about multiplexer, encoder, decoder. We will discuss in later part of the video. And we also deal with code converters. Now, when we talk about code converters, we are talking about binary. We are talking about binary coded decimal or 7-segment display. Okay, so in this case, you can see that when we talk about a 7-segment display, we are talking about 8-bit information: 0, 1, 2, 3, 4, 5, 6, 7, and 8, and 9, and 10. But 10 is not considered, so we are considering from 0 to 9. But how this can be used in making certain kind of traffic lights? How can we incorporate different type of flip-flop? This we can do with the help of sequential circuits. So now I hope everybody is clear that what is combinational circuit, what is sequential circuits, and how they can be segregated on how many parameters, on which parameters. So I hope this is clear. When I talk about combinational circuit, the first point we were discussing about adders. So when I talk about adders, because we are dealing with digital electronics, so we are having a binary adder. This binary adder can be half adder, can be full adder, or it can be parallel adder also. We will talk about this also. Because when we talk about parallel adder, we are talking about look ahead carry. As you know very well, in the case of half adder, I also discussed some of the concepts in the previous lecture, in which I was talking about the full adder deals with a carry. When anybody asks you what is the difference between half adder and full adder, just tell very clearly. In half adder, we are talking about 2 inputs, and the full adder, we are talking about 3 inputs, where the third input represents your carry. Okay, so we will also discuss the ripple carry and carry save and look at carry. These are different types of adders we can see from the parallel adder. Now let's talk about half adder. So half adder is a type of combinational circuit which will have 2 binary inputs. That's all I discuss, and will deal with the sum and carry. So 2 kind of inputs can be. Now you can ask me, sir, why this carry is there? You already told that in the full adder we will have a carry. See, in the full adder, we are talking about carry as an input. But in this half adder, we are talking about the carry as an output. It will be more clear by seeing a truth table of the half adder. You can see over here. In the truth table of the half adder, you can see both 2 inputs are there: 0, 0, 0, 1, 1, 0, and 1, 1. In 1, 1, we are having a carry. Okay. And you can see easily that in the sum, we are having about A bar, B plus AB bar. That is, we are talking about simple as a XOR gate. And when we talk about XOR gate, one thing need to be understand that when we talk about XOR gate, whenever the inputs are not identical, I'm repeating, Whenever the inputs are not identical, then your output would be there, otherwise no. Okay, not identical, I'm again using the word. Similarly, you can see over here in this case that we are having C A bar B, and you can see whenever the inputs are not identical, we are getting an output, otherwise you're not getting an output. And carry is nothing but a representative AND gate. So this is a very simple logic diagram. You can make an half adder. You just have to provide two inputs and two gates are there. Over here, one more thing I just want to emphasize. One trick is there. Whenever you are going to design any kind of adder, see, you have to understand two things. One, how many inputs? On the basis of inputs, the number of gates would be decided at the input side. And on the basis of output, the number of gates would be decided at the output side. Now, in this case, you can see that we are having a two inputs, so two gates were there. Similarly, when we talk about full adder, now you can see in the case of full adder, we are having three inputs, where third is nothing but carry input. Okay, and we are talking about carry output and sum, because in the full half adder, if you remember, we were only dealing with carry and sum. We were not dealing with carry input or carry output, because there was nothing kind of carry existing in the case of input and output. So we take carry input as an C in, we are taking an input, and carry output we are taking as output. Now you can see we are taking two inputs, but don't confuse yourself how the carry would be there. If you see very precisely on this truth table, you will come to know that I am writing from 0 to 7. I hope this is clear. I'm using from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7 in the decimal value of 7. And I converted into binary. So I am going from 0 to 7. That's why I'm using 3 bits. Okay. But if I'm talking about, say, if I want to go more than 3 bits, then I will talk about another kind of adder. I hope this is clear. Simple sum, and sum is taken out. 0 plus 0 is 0, 0 plus 0 is 0, and the carry is 0. Let's take any other example. 1, 1, 0, where we are talking about 1 plus 1 is 0. You know very well. Sum is 0, but the carry is 1. Right? You can take another example. All values are input as 1, all 1. 1 plus 1 is 0. Remember, 0 plus 1 is 1. So carry is also 1 and sum is also 1. Right? So I think now the clarity is there that we don't have to remember what is the value of carry input. Just try to write from 0 to 7 in all the inputs, and sum and carry would be designed accordingly, or would be obtained accordingly. Now, what I was talking about, you can see the logic diagram of full adder. Now, I was talking about 3 inputs, so 3 inputs are there, 3 gates are there, right? If you're talking about this way, you can ask me, so this is the 4th gate. No, this is not the 4th gate, because that is representing a sum. So these 2 gates are representing your output, and these 3 gates are representing an input. I hope this concept is clear. So now what we understand what is half adder, what is full adder. Even though we can make from 2 half adders 1 full adder. Okay, you can see 2 half adders are there, but yes, they need to be connected in a cascaded form. Now let me go a little bit of cascaded. Those already saw my previous videos, they might be aware of it. What is the difference between cascaded and coupling? But I will repeat again. Those are new to this video, new to this channel. See, when I talk about cascaded, I'm talking about the output of one would be same as the input of second. I'm repeating, please. The output of first would be the same as the input of second, that is a cascaded. But when I'm talking about coupling, that means there would be any kind of element between your output of the first and input of second. And if it is so, that is your totally coupled. So coupled means the output won't be same as the input, but in the case of cascading, yes, it would be. Okay. So you can see that in the full adder, you're using 2 half adders, and this can be done. So I hope everybody is clear about the half adder and full adder. So next type of adder we are going to discuss is nothing but BCD adder. So when I'm talking about BCD adder, you already know very well that is the binary coded decimal. So when I'm talking about binary coded decimal, that means I'm not talking about any kind of value, but I'm talking about BCD, that is binary coded decimal adder. So we have to, it is very clear that we are going to use 0 to 9. And we are going to use weighted code also, because we talk about 8421, access 3 code and 8421 code that we already discussed in the previous lectures. So 8421 code, that is naturally having a weight. Now how it come out of 8421? 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. That means in this BCD code, you will see that's a very good thing in BCD adder. Okay, we will talk about 0 to 9, because we already know that decimal value is 0 to 9. 10 is not a decimal value in coming out of the BCD, right? So we are talking about 0 to 9. So whenever we are getting more than 9, the BCD adder would behave in a different way. You can see conversion and coding. So if I'm talking about the conversion, you can write 12 in a 8421, but in this BCD, no, it cannot be, because 1 would be written separate and 2 would be written separate. I hope this is clear. This is your 1, 0, 0001. You can solve it as a binary and divide by 2, and this is your 2. So this is BCD code for your 12. Now how it will work, you can see that we are having address buses, and we are having we are representing two different input that we are representing. Say two numbers are there, so we are representing A0 to A3 because we are using 4 bits. Similarly, we are representing B0 to B3, again the 4 bits, and these are the select lines S0, S1, S2, S3. It will be more clear when you will see multiplex and demultiplexer. Okay, so one algorithm we follow in a BCD adder, the 4-bit BCD adder would be there representing 0 to 9 bits or 9 digits, you can say, more specify. So adding BCD number is in BCD addition. So if your adding is going more than exceeding 9, we will generate a carry, and by adding 6 to sum. So it would be more clear. Let me show an example. You can see addition with a BCD number. So it is basically you want to add 9 plus 9 plus 1. It will be 19. So again, we will take for the carry from the previous digit. Now it would be more clear from this over here. Now I am talking about 0 to 9, right? I am taking a switch. Now just see to it. Don't try to remember it. Just see it. 0 is 0. This is 1. This is 2. This is 3. This is 4. This is 5. This is 6. This is 7. This is 8, and this is 9. Decimal value. So what these select lines are representing, don't confuse yourself of what should be the value of S0, what should be the value of S1, what should be the value of S2, what should be the value of S3. Okay, the carry output is 0 when I'm talking about 0 to 9 decimal value, and S0 represents the minimum weightage value, and S3 represents the highest weightage value, and I just write 0 to 9 in a particular 0 to 9 weight or 0 to 9 values. These are my select lines. But whenever it is exceeding more than 9, now I'm talking about 10 to 19, so the carry would be high. The carry would be turned high. Okay, but see over here, again I am writing 0 to 9. I hope this is clear. The select lines are not going to depend on the decimal value, because it depends upon the carry value. If the carry is 0, it would go to 0 to 9, and when the carry value is high, it again goes to 0 to 9. I hope this is clear. So remember, the value of carry or the value of extra input you are providing, that would play a picture. Now see over here, it would be more clear now. I'm giving a value, and that you are going, when you're going to more than 9, I'm going to add plus 6, and it would behave in the same way. Like you can see, this is your 10 to 19, and when I'm talking about this is being shifted over here, because when it is turning 1, it is going back. Okay, so it is going to get plus 6, and binary sum, it is going to BCD adder sum. I hope this is clear. So what is the algorithm for BCD adder? They are one algorithm that if the sum is up to 9, use the regular adder, no problem at all. But if the sum is greater than 9, use the regular adder and add 6 to the result. Have an example. Now I want to add, you can see this is 5, this is 6, and I'm adding 11. I should get 11. This is 11. You can check out 8421. But this is an invalid BCD number. So if you are looking for a valid BCD number, add 6. And then you will get an additional bit value. See, don't confuse yourself with a signed and unsigned value. Okay, because you know very well that when I'm talking about unsigned value, or when I'm talking about signed value, when I'm talking about negative number, then the second complement comes into the picture. It has already been seen in the that I've discussed in the previous video, or we also seen with the help of practical implementation that signed value will come into the picture or negative value will come into the picture whenever we're talking about 1 or 0, the extra bit. Otherwise, if you are going to add over this, you're going to add 6 and you're getting a valid BCD number, but if it is exceeding more than 9. So when the result is more than 9, you know very well that we have to carry out the value of k, and as already shown in the previous slide. I hope this is clear. Anybody having any kind of query, they can reply in a comment box. I would be more than happy to answer it. Right? Is this clear? I hope this is clear. When the result is more than 9, I'll discuss in detail with the help of slide in the previous slide. So when I'm talking about 4-bit BCD adder, right now we are talking about only combinational circuits. Okay, so the next part of this combinational, next part of this sequential circuit or the sequential circuit we'll discuss in the next video. So when we're talking about combinational circuits, you can see that we are talking about 4-bit BCD adder. When I'm talking about 4-bit BCD adder, you can check out that in this case, I'm using how many gates I would use? I would use 2 gates for input and 1 gate for output. As you can see over here, the K is representing your carry bit, whether it is 0, whether it's 1. So 4-bit adders you are using, so that actually the inputs would be 4. But 2 inputs are combined together, so 2 inputs will be taken out. This is a half subtractor. Again, very simple half subtractor. You know very well that the 0 minus 0 is 0, 0 minus 1 is 1 with borrow 1. 1 minus 0 is 1 with borrow 0, and 1 minus 1 is the difference is 0 and borrow is also 0. So you can also solve through K map, right? Many of the questions I asked to a student about the K map, rectangular K map or triangular K map, and the students are very much confused about this. See, students, you don't need to worry about what is K map is all about. You have to understand what K map is all about. Don't worry how the K map would operate. Just understand what K map is all about. If I ask you that I want to make a K map for a 4 variable, how many rows and columns I would have? I would have 4 rows and 4 columns. I hope this is clear. So understand this, that K map is only used to simplify your complex values, or complex relations, or complex structure, or complex what I can say complex values for the different kind of like you are having a more than 4 variable, or more than 8 variables, more than 10 variables, then it is very difficult to solve through Boolean algebra. Then we are going through K map. Okay. Similarly, the same concept is there. 2 inputs, 2 gates, that's it, and the output is also 2. Again, full subtractor, same case over here. You can see, don't confuse yourself again. The inputs is again we are writing from 0 to 7. Difference is there and borrow is there, so you can easily over there and you can check out using a K map. You can see we are talking about that D, that is the difference, A XOR plus B XOR plus. Is a full subtractor. You can design, you can now understand one thing, that the relation you can obtain. Okay, but the thing is very important that over here we are talking about the circuit diagram of the full subtractor, but we are keeping a borrow and difference accordingly, right? So again, anybody can ask you how many half subtractor are required to make one full subtractor. So 2 half subtractors are required, one full subtractor. Similarly, 2 half adders are required in making one full adder. So I hope now the adder and subtractor concept is clear to everybody, because now we are going to move to a different concept, that is nothing but a multiplexer. So when I'm talking about multiplexer, it is a overall a new thing, because you can see my previous video in which I designed a multiplexer and on Tinkercad using different types of gates. Okay, but if you talk about multiplexer, remember one thing, as the name suggests, we are going to have one output and many inputs we can have. Now when I talk about many inputs, there should be some relationship between them. So we are talking about 2 raised to power n. So if the output is 1, 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, and all this. So naturally the select lines also play a very important role. Okay. So the relationship is very important. Capital N is equal to 2 raised to power M. So if I talk about different type of mux, we are having 2 is to 1, 2 is 4 is to 1, 2 raised to power 2. So if I'm talking about 2 raised to power 2, that means I'm having 2 select lines. 16 is to 1, so that means 2 raised to power 4. I'm having 4 select lines. 2 raised to power 5, that means I'm having 5 select lines, and so on. So by the concept of input, we can easily design, we can easily select that how many select lines would be there, and we can design any kind of multiplexer for the same. Now, if we're talking about 2 is to 1 mux, this is the representation of the multiplexer. So you are having 2 input lines and 1 output lines. And how many select lines you will have? Because 2 inputs. So 2 raised to power 1. So only 1 select line. I hope this is clear. Similarly, I have talked about 2 is to 1 mux. You can say the slack line can be 0, then I have output would be I0. And when the slack line would be 1, because that only 2 type of permutation combination we can have S0 and S1. Right? So the output would be seen as S bar I0 and other one is S. Similarly, if I talk about different types, let's say I have 2 select lines. Then I would have S0 as S0 bar S1 bar, then S0 S1, then S0 bar S1 plus S0 S1 bar. That means I am going to repeat it. So 4 different type of permutation combination I would have in my when I'm having 2 select lines. You will see in a 4 is to 1 mux multiplexer in which you will have 2 select lines in front of you. So again, how many inputs I am having? I am having 4 inputs. The output is 1. How many select lines I would have? 2. Right? Because the 2 raised to power 2. You can see I would have in the first input when the first output when I will get one first output I naught. The relationship is S1 bar S0 bar. When I will move to second output, it would be S1 bar but S0. Then third output I2, that is S1 S0 bar. When I will talk about fourth output is S1 S0. So you can see because 4 inputs are there, then 4 and gates would be there. Don't count these NOT gates because these NOT gates are for the select lines and 1 output would be there. So 1 OR gate would be there. How many, if I want to make 4 is to 1 mux, can I make it 2 is to 1? Yes. How many 2 is to 1 mux I would be used? I would use 2 mux and 1 for the output and 2 for the input. Similarly, if I want to make 8 is to 1 mux using 2 is to 1 and 4 is to 1, so naturally I will use 4 is to 1 at input and 2 is to 1 at output. I hope this is clear. Similarly, you can make 2 is to 1 mux. If you want 4 inputs, then you have 8 is to 1. So you will have 4 at the input, then 2 would be combined and then would add 1 at the output. I think is it clear? So when I already told you that when we entered in the mux and demux, we are entering into a different kind of concept building. Sorry, I'm not well today, but the student requested, so I'm making this video. Sorry for the inconvenience whenever this cough is coming. So when we're talking about demultiplexer, multiplexer is totally opposite to the multiplex. In multiplexer, we are having multiple inputs and the output is 1. When in the case of demultiplexer, your input would be 1, but output can be many. Again, the relationship is same, 2 raised to power n. You can see 2 in the first, when you can see over here, it is written there 1 to 2. Input is 1, that is fixed. Output can be 2, that is 2 raised to power 1. So if it is 2 raised to power 1, how many slack lines? 1. When it is 2 raised to power 2, how many slack lines? 2. When it is 2 raised to power 3, how many slack lines? 3. And when it is 2 raised to 16, 2 raised to power 4, how many slack lines? 4. So I hope this is clear. So this is how we are making a demux and mux. So we were discussing about demux. So you know very well that I already discussed that it depends on the number of select lines. So you can see 8 to 2 raised to power 3, 1 to 16, that is 4 select lines we have. Right? So this we already know to it. You can see the function diagram of demultiplexer in which the input is 1, the output can be many. And the relationship I already discussed with you. I already told you that we are having 2 raised to power n. You can say in certain books it is written 2 raised to power m. Doesn't matter. We are only concerned about that how the select lines and how the output input relationship can be established. So this is how the symbol representation of demultiplexer in which the input is 1 and the broader at the output. So over here, I just want to take your attention that we might use see nozzle and turbine. So just answer me in a comment section that multiplexer is looking like nozzle or a turbine, or demultiplexer is looking like a nozzle or turbine. Okay. So you can see that 1 to line demultiplexer, you can see 2 inputs are there, and you can see the NOT gate we are going to use for select lines, and the 2 outputs that are there, because we are talking about 1:2 demultiplexer. So it is totally opposite according to the multiplexer, right? Again, 1 to 4 demultiplexer, when you talk about line multiplexer, the input is 1, output can be 4. You can see D0, D1, D2, D3, and again, there is no need to cram it. Just see, in the previous truth table, we are having 0, 0, and 1, 1. These are the available one. We are giving as an input that can be used as a clock also. So we are taking 0, 1 and 0, 1, 2 permutation combination we're talking about. You can see all 0, then 1, 0, and then all 0, and then 1, 0. Because now understand one thing. What you understand from over here, when it is on, when input is on, then the output would be reflected. It is independent of your input. I hope this is clear. I hope this is clear. Your input was 0, so output 1 would be 0, but it is on, so your output would be shown over there. In this case, the input was there, but the clock was 0, so output would be 0. Input is on, output clock is given, or in is given. So what we can say, our slack lines is 1, you can say, because you will see more of the clock in the sequential circuit. So slack lines is given, so output is 1, not 0, because one output can be on only. 2 outputs cannot be on in any case of in the case of demultiplexer in this truth table. Now let me see. I'm giving a 1 I over here. Input is 1. I'm having a slack line because 2 slack lines now. 2 is to 4 line demultiplier, 2 raised to power 2. 0, 0, 0, 1, 1, 0, and 1, 1. You can see D0 has a lowest value. D0 is on. The D1, then D2 and D3. Diagonal, all the values, data values would be on. I hope this is clear. So 4 outputs, so 4 AND gates would be used. Similarly, in 1 to 8 multiplexer, you can see 0 to 7. 8 AND gates are used, and the different slack lines can be seen. You can see S0, S1 bar, S0 bar, S1 bar, S0 bar, S2 bar. And similarly, you can change the permutation combination for the slack line as I already discussed with you. The truth table, if you talk about 1 to 8 demultiplexer, you know you have to D0 to D7, right? So D0, then D1, then D2, then D3, then D4, then D5, then D6, and D7. I hope this is clear. And if you see over there in these slack lines, S0, S1, S2, S3, sorry, S0, S1, S2, it is written as S3, is it S2? You could write S3 also, not a problem, but keep a pattern S0, S1, and S2. I'm writing from 0 to 7, right? So I'm not using a whiteboard over here. If anybody want explanation of whiteboard, I would be more than happy. I will use the next video a whiteboard and explain to you. But I hope this is well explainable as I explained to you, giving a trick to writing a truth table for different multiplexer and demultiplexer, multiplexer, demultiplexer. Now we are going towards another combinational circuit, that is nothing but encoder. I hope everybody is clear about adders, subtractors, multiplexer, and demultiplexers. So we are talking about encoder. When I talk about encoder, it's a type of combinational logic circuit, definitely, but it is opposite to the decoder. We will see that what is decoder is all about. Okay. So we're talking about encoding and decoding. Decoding, you know very well when you decode something, right? Encoding, when you make a QR code, when you are, putting some kind of data which is hidden, which cannot be encrypted, which cannot be seen. Okay, so that is basically the basic concept of encoding and decoding. You can see M inputs you are having an outputs, right? So we are having different encoders. You will see yourself over here. We will discuss, right? But we encoders are basically used to translate the linear motion into a digital signal. I'm again repeating, there is a difference between digital and discrete. Discrete is the original form of signal, whereas digital is a signal as per our convenience. Okay, so we are having decoding, that is decoded binary output, as a while encoder has binary code as an output, right? So electronic device which convert analog signal, certain books you will see this kind of definition also. The encoder which converts the analog signal digital signal. Okay, but I'm not more emphasizing into it. You will see yourself what encoding is all about. So we have four different types of encoder. One is priority encoder. We are having decimal to BCD encoder, octal to binary, and hexadecimal to binary. So more emphasis on binary only. So when we talk about encoder, you can see M is equal to 4. What is M? What was M? M was your input. If you don't remember, I will take you back. Just see over here. M as an input and N as an output. So M is 4. So 2 raised to power 2. How many slack lines I would use? 2. And the output would be N output. You will see yourself. Priority encoder. How many inputs? 4. 2 raised to power 2. How many slack line I can use? 2. The output would be 2. Okay. So the major difference we normally see over here in this case, two outputs as a priority encoder. Now priority encoder, the name suggests over here, the priority would be given to a certain input, a certain line, and the input line with the higher priority shall be considered. See, if two inputs are given at the same time, then the input line with higher priority would be considered. Now you can see that we are having D0 to D3 all 0. So output, you can see that there is no output. But when I'm giving 1, the output would be 1. So why not y1 is 0, but we are getting a 1. Again, the d1 is 1, so 0, 1 is would be given and the output is 1. So accordingly, we can decide what is the priority you are having this over here. Okay, that can be also designed or explained using K-map, but I am just giving an overview that what priority encoder is all about. Okay, so if you're talking about all 0, you are getting an output as 0. If you're talking about 0, 0, 0, 1, so basically we are giving a cross condition, we are giving an extra condition. If you remember, don't care condition in your K-map also, when we were discussing the K-map in the previous lecture. This is logic diagram parity encoder. You are getting an output. You can make any of the C. You already know very well that when this output and input relationship is given to you, how can you make using a basic gates or universal gates? So you can also make through it. There is no need to explain over here, but I think you wrote it down. If you still feel any kind of problem, I can make another video on implementation of logic gates and making a simplification for the same. This is decimal to binary encoder. You know very well the input would be 0 to 9 because decimal at the input side, and output side we are dealing with BCD encoder. So how many output we will have? We will have 4 outputs, that is 8, 4, 2, 1. So very simple again. We are giving 0 to 9. So whenever the 0 is on, we are giving 0 as a 1. When the 1 is on, we are giving 1 as a 1, and so on till 9. Similarly, you will get all 0, then 0, 1, then 2, then 3, then 4, then 5, then 6, 7, 8, and 9. So we are converting from decimal to value to BCD output. This kind of logic would be used when you are going to design a 7-segment display, or you are going to design a home automation system using some LDR or photoresistor. Okay, this is very, very important. In fact, this can be shown through experiment also. And if you feel so, I can make a video on that, right? But we already discussed in detail about this in the previous lectures when we were discussing about the basic concepts of the digital electronics. You can go and check over there. So when I talk about DC decimal to BCD encoder, already the concept is given that whenever the zero is one, so one the we will have this one only D is only the all are zero. Whenever the one is given, then only D is on. So automatically you can design this circuit for the same. Octal to binary encoder, how many inputs we would have? We would have 0 to 7. And how many inputs, how many output we will have? We have 3 outputs. Again, it depends about 2 raised to power 3. Right? So again, the concept is exactly the same. When the 0 is on, we will have all 0. When the 1 is on, we will have 1. When the 2 is on, we will have 2. When the 3 is on, we will have 0, 1, 1. When the 4 is on, we will have 1, 0, 0. But overhead, we will talking about only 3 bits. We won't talk about 4th bit. Okay, don't keep X, Y, Z, and S. And keep X always 0. No, we will only use 3 bits because we're talking about octal. So we're talking about 2 raised to power 3. This logic diagram can be designed. Now we're talking about decoder now. So I already discussed about this. It's a decoder is opposite to the encoder. And we have inputs and output slack lines and label line can be designed using certain slack lines and certain conditions, permutation and combination. So it is totally opposite to the encoder. So you can see that we are talking about overhead 2 is 2 and 2 raised to power and decoder. So if you are having 2 inputs, so the decoder, the output would be 4. So it's a 2 is to 4 decoder, you can see. Now, you can see that we are having 2 is to 4 decoder. So if we are having a 2 is to 4 decoder, how many inputs? 2 and in the form of select lines. Okay, so Q dot would be S1 bar, S dot bar. It is totally up to you. It is not confined that Q dot has to be S dot bar, S1 bar. It can be different also. But we have to remember that all the slack lines need to be incorporated in a particular pattern. Similarly, 3 is to 8 decoder, the inputs are 3 different slack lines. You're right, we are going to write 0 to 7. And similarly, when Q at all 0, Q dot would be 0. Then when 1 is there, Q1 is on. When the 2 is there, Q2 would be on. And all the diagonal elements would be shown over here. I'm showing you, I am telling you the trick beta. I'm not going to the detail that how the decoder and encoder are to be designed, what is the the implementation and the circuit diagram. I'm just going to give you tricks and overview of all this. Still, if any student want a detailed explanation about any kind of topic, they can comment it to it. So I can I would reply to it and I would try to make a video on this for the same. The last we are talking about magnitude comparator. Very, very important combinational circuit. In the next video, we will discuss about sequential circuit, but in this video, we are only talking about combinational circuits. So when I talking about magnitude comparator, we are talking about the classification and the definition. So you can see that we are having an identity comparator and we are having a magnitude comparator. So it can be add bit or you can have 3 operations, A less than B, A greater than B, and A equal to B. So these comparators can be 1 bit or 2 bit, depending on the inputs. If your inputs are 2, it would be 2 bit. And if the input is 1, you are having a 1 bit. So first, let's talk about first 1 bit magnitude comparator. So when I'm talking about 1 bit comparator, you can see we are having 2 inputs in 1 bit. And we are having two different inputs. At 0, 0, you can see 0, 0, 1, 1 and 0, 1, 0, 1. It is randomly taken. In the output, what are the different output we can have? A less than B, A greater than B, or A equal to B. These are the 3 output we can take. And accordingly, you can see 0 is equal to 0. So it is 1, all are 0. When we are talking about 0 and 1, so we are talking about A less than B. Yes, it is 1, other are 0. When we're talking about 1, 0, we are talking about A greater than B. Yes, it would be 1, all are 0. And when it is identity comparator, the last row is basically showing your identity comparator. When you're talking about 1, 1, so A equal to be B, otherwise others are 0. So this 1-bit comparator can be designed. You can see that this can be designed using different circuit diagram, different logic gates. Not necessarily that you have to follow this. Okay, so you can see, as I told you, this is done with the AND and XOR gates. Earlier it was done with the AND gates. When I'm talking about 2-bit magnitude comparator, that means I will take two sets. So your inputs now divided to A dot and A1. It is A dot actually, and B dot and B1, which is nothing but B only, and three inputs would be there. Three outputs would be there. So in short, we are taking a 4 inputs only. So you can take A dot, A1 and B dot and B1. Right. So we write accordingly 0, 0, 0, 0 and 0, 1, 0, 1. So how we are going to see? We are going to add them. Okay, we are going to add them, and accordingly you can see. Now you can take, let's take a second option in which we are having 0, 0 and 0, 1. 0 plus 0 is 0, but 0 plus 1 is 1. Right. So we can say A less than B. Yes, that is 1. Right. In the uppercase, all are 0, all values are same, so it is A equal to B. Let's take a case of 1, 1 and 1, 0. 1 plus 1 is, just tell me, 1 plus 1 is 0. And 1 plus 0 is 1. But 1 plus 1 is 0, but with carry 1. So A would be higher, so it is A greater than B. Let's take a case one more. 1 and 0 and 1, 1. So 1 plus 0 is 1, we know very well. Right? But 1 plus 1 is 0 with carry 1, so A would be lesser. So in this way, we can discuss the 2-bit comparator and different realization can be carried out. So over here, students, I'm stopping for this video in which we discuss about combinational circuits, in which we discuss how the combinational circuits can be a part of sequential circuits. In front of you can see a sequential circuit in which the combinational circuit and memory are being combined together, where the memory is a feedback and more primarily that we are giving a clock signal, and this clock signal can be synchronized and asynchronized, and on the basis of this we decide a sequential circuit. In this video we also discuss about different adders, different subtractors, multiplexers, decoders, encoders, demultiplexers. Even we also discuss the magnitude comparator with different realization of the universe, with the different realization with the help of universal gate or basic gates. Still, if any kind of query of the student is left or they are not very much clear, they can write in a comment box. And in certain points where the previous video we already discussed in detail about the basic concept, the students can go to the previous video, can check out. I also uploaded what the practical implementation and practical and how we can make a multiplex or Tinkercad. So this you can also check out. Right? So any kind of query, beta, you can write in a comment box. Keep subscribing so that you can get each and every information over there. Thank you, beta. Thank you.